Here we're reacting an alkene with an acid, where X is halogen, like any of these. So how do we predict this product? Well, we see this double bond, this pi bond, is going to come in and take the hydrogen from the acid, forming a positive charge on this carbon here, a carbocation, so to say, and a negatively charged halogen, one of these. Then one of these lone pairs is going to come in and attack the carbocation, forming this right here. Pretty easy. I've added a methyl group here at the end of this carbon. How do we predict the product? Well, the same thing is going to happen. The pi bond is going to come in and steal the hydrogen. And a carbocation is going to form on this tertiary carbon. The most stable carbocation will always form. We put in the halogen, it's going to attack, and we get this product here. Here's the stability rankings of the carbocations. The tertiary is more stable than the secondary, is more stable than the primary. The most stable carbocation will always form first. This is always the case. Knowing this, can you predict the product here? What will be the product? Pause the video, give it a think. Think it over for a second. This is the product. The halogen will always go to the most stable carbon. Always. What about here? What will be the product here? Think over. Pause the video if you need to. This is the product. The secondary carbocation is what will be favored, not the primary, not this one. Secondary. Here's another problem for you. You can probably already tell what the product is going to be. It's this, right? This is what is called the Markovnikov product. What about here? How will this add to this? It won't actually add to this tertiary carbon here. This is actually the seen product. This is called the anti-Markovnikov product. This is what it looks like in solution. Because this group here is larger than this group here, it will add to the less stable carbon, giving us this. Once we have a compound like this, we can use a base like sodium hydroxide to kick this group off, giving us this product. Let's predict the product here. Let's think about it sterically too. Where will this acid add to this alkene? Pause the video if you need to. The acid is going to add to this side because it's more accessible. This side of the alkene will be physically closer to the acid and therefore add here. Let's go through this problem now. Where do you think the acid is going to add? Pause the video if you need to. It will actually not add here, but it will actually add here because this carbon is more stable. And we get this product. From this, we can denote that stability always beats sterics. Here's another practice problem. Where do you think the hydroxide is going to add? It's going to add to this carbon here, giving us this product. Here we have a Diels-Alder reaction, giving us this product. And then we're going to add some acid. Where do you think the halogen is going to add? Pause the video if you need to. It's going to add to this carbon here. So let's draw that product. Like so. Here we have very few of these compounds right here and a lot of acid. So where do you think the halogen is going to add here if there's more acid than alkene? It's actually going to add everywhere. So we're going to have this, and this. Pretty simple. There's more acid than alkene, so it's going to add everywhere. Now you know the reaction between acids and alkenes. Good job.